parsing, they actually use an external library, and so it's a little bit hard. I'd have to check, let me put it that way. But given how few lines of code we have, note these lines of code here also include like lines of proof. Given how short these are, it can't be that much worse, right? At most, it's 180 times worse for that. It's only 40 times worse for ARP, which is a little tongue-in-cheek, but yeah.
So how many of those lines of code are for specs?
Oh, yeah. So, yeah. So let me, can I do this easily? I will show you, I flashed a spec for IP earlier. Here is the spec for IP. So you can imagine this is actually probably our longest one. So how many lines is this? 1, 2, 3, 4, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 lines. There is, those lines of code also include the import statements for the library. So if you hack those, I mean, yeah, it's not bad. Also the definition, I guess there's this definition of this sort of weird calculate length of packet header function. That's probably another like 12 lines. It's doable. Any other questions? Okay.
Here.
What? Oh, yes.
How big can be your LTACs for deriving?
How big can the LTAC be? As long as big as you want. I don't.
I mean, in your code base.
So, are you talking about the LTAC, the scripts that do the synthesis, or the tactics that get called by that tactic? Does that distinction? So the actual synthesis tactic. Let me skip to the end here. Is for all of these, it's a one-liner. But of course, hidden under that one-liner are many other lines of LTAC. So if I had to quantify the total number of LTAC that is hidden in the library for all of the formats and combinators that are used in the synthesis function, it's probably on the order of 1,000 lines of LTAC, maybe, I would guess. Yeah?
So then if the IP specification is only those 16 lines, that's the 12 lines or whatever, and one line of proof, then what are the other 100 lines of code?
Yeah. No, that was the line of proof for synthesizing the decoder. It turns out that there are some extra proof obligations you have to satisfy and add to a hint database in order for this to work. They have to do with, so it turns out when you calculate the IP checksum, you need to actually know exactly where the IP checksum is when you calculate it. So there are proofs showing that that IP checksum always occurs in a fixed location. And that actually involves a little bit of gross manual proof effort, for better or worse. So the bulk of the proof effort is in that. Yeah, question?
So I guess the examples of variable length data all have like an explicit fuel argument. Is it possible for the framework to handle like arbitrarily long, like for example, null terminated strings?
Yeah, that's actually one of our, I should have called that out, but where is it? Yes, we actually have those variants for the null terminated strings and list special special character terminated lists. But for some reason, I haven't put it up here. So they exist. Yes, it's possible for it to do that. Yeah. There's also, I think there's another variant in the library that takes, instead of the number of elements to decode, the number of bytes to decode, which is necessary for some other weird formats. But there are a number of different ways of encoding fuel, it turns out, for whatever reason. I don't know. Any other questions? Okay.
I have
one more. Okay, yes.
Actually, for example, if you are encoding, so the network Indianness in IP is big Indian, right?
Yes.
So if I am encoding from my little Indian machine, but I want to decode in a big Indian machine, and the inverse will not encode, I will not get the same thing back, right?
Yeah, I guess the proof of correctness is in terms of a common source data type. And so you would need a format for the big Indian machine, and you would have a format for the little Indian machine, and they would reflect the difference of these source data types. And I suppose once you've done that, you could prove, it should be trivial to prove that there's a it should be easy to prove that there's a conversion between the big Indian and little Indian format. You could do like a full proof of correctness that way. And of course, it would compose nicely, I think. But you're exactly right. The correctness is in terms of your particular view of the source data. Yeah. Okay. Well, I've got 3 minutes left, so I'm going to give a shameless plug too. So I'm from Purdue. I'm an assistant professor there. I started 2 years ago. There are many more people doing PL at Purdue. In fact, there are 10 of us, and soon to be one more. They're spread across 2 different departments, and we do all sorts of crazy stuff, mostly involving PL, as you might expect from PL faculty. But we have people working in formal methods in Coq, like me. We have different flavors of formal methods. We have theory B people, synthesis, compilers, metaprogramming, PL theory. We have people doing security plus PL, binary analysis, static analysis, on and on. We have people doing PL plus ML, and this is machine learning. Sorry. I had to throw it in there. So what's the take-home message? If you're an undergrad or master's student, you're thinking about grad school, please consider us. There are many other people at Purdue you could work with, but take a look. We have this sort of overarching purple Purdue PL group. We have weekly meetings, yada, yada, which means because there's this overarching group, of course, we have a social media presence, and you can follow us on Twitter. And I should actually take a picture, sorry. Okay, I'm going to do that in a second. And you can follow us on Twitter. You can @ us or follow us on Facebook. And I'll save this selfie for after I'm done talking. Okay, in conclusion, so hopefully the takeaway for the people in this room is that if you forget all the details, at least I hope you remember that Coq is actually a very powerful tool, not only for writing software by hand and verifying it semi-automatically, but it's also a very powerful tool for automatically deriving correct software. And this is, in fact, software that is usable in the real world, meeting real-world specifications. And of course, once you've done that, as I said before, these proofs can be used to integrate as part of a larger project, some other system you might be developing. It's great. I mean, what's not to love about Coq? I'm probably preaching to the choir, but we've got this powerful specification language that allowed us to embed these formats and these specifications of correctness without too much difficulty. Galena is a pretty good functional language, all things considered, and we can write our implementations in this familiar functional style that everyone's probably familiar with. And these tactics, the LTAC is a really cool, powerful metaprogramming language for automating the construction of well-understood terms. What did I mean by that? I mean, we can, in much the same way that we can build proof automation that solves similar proof goals, we can build up automation that derives similar sorts of software. In the case of these, in the case here of these decoder encoders, we have this well-understood domain, and we can actually automate the derivation of software in it. And you too could write some sort of automation for deriving software in your own domain, and then integrate it as part of a larger system. Anyway, if you're working on verified distributed systems and you have some serializer and deserializer code as part of your trusted code base, you should come talk to me, and I can help you take that out of your trusted code base, hopefully. And I'm also happy to talk if you're not interested. If you're not working on distributed systems, if you're not interested in talking, then we don't have to, okay? And I'll end asking for questions and taking a selfie for social media something, okay. So you can clap while I do this. Oh, sorry, I shouldn't have said that, okay. Okay. Okay, I do actually have some more questions. So, yep. And I guess back first.
Hello.
Hi.
Have you tried using or defining combinators that work simultaneously on the encoder and the decoder, or even simultaneously on the type definition, the encoder and the decoder?
So I mean, yes, we've done it for the simple example, like that simple context-free example, a case study that does that. We could imagine doing that. We could just take this and plop it into what you're doing. I haven't done that, but it could work. And then you could get automatic serializers and deserializers based on the type. I mean, one of the real motivations here is we're trying to avoid prescribing a format. I want to take the format from somewhere else. And so one of the downsides if you're type directed is you lose you're sort of dictating the format based on the type as opposed to having it dictated to you, which I guess doesn't sound as appealing. But I will note that my student Chen Xuan has actually implemented a protobuf compiler using Narcissus, and there we actually generate the types and the serializers and deserializers based on the types that you give there. So maybe I guess that would be an answer to that, is that's an example of using the types to generate the functions. There was another question. Yep.
How happy are you with LTAC? I mean, is it easy, difficult, seamless, nasty?
I mean, what is happiness? I don't know.
Did I mention that Ben lived for 2 years in Boston and worked with Arun Chipala?
Yeah, I think Leonard just answered the question, right? No, I mean, Maybe we should get a beer to discuss it. I think LTAC is actually very good in general. My only real complaints with LTAC come when it's time to debug it, both in terms of getting weird behavior and performance. When there's LTAC performance problems, it's very hard to track them down, and then it's time to bring in some reflection. So I think if you look at like Gregory Malika's work on his mirror shard, mirror core, I think these more reflection-based tactic approaches have a lot of potential too, but they're not without their downsides because there's even more, what is the word, learning gap, whatever that is. So reasonably happy, I suppose. Yes?
So your decoder and encoder, as you mentioned earlier, have a source and a target. And so it seems like your decoder and encoder are merely home sets in an appropriate category. So have you considered a categorical perspective in solving this, some of the issues you discussed?
So the question was, have I considered using category theory to help solve some of these questions? And the answer is I'm not as much of a category theorist as you might expect from, well, I don't know why you would expect that, but no, not really. But it's an interesting. It could, I think, it could offer an interesting perspective on the problem. Yes.
Your nice proof application is at a sufficient generality, the notion of isomorphism. So
yeah,
it makes some things easier or clearer.
Yes, sure. I think there is again, because we are just talking about arrows between objects here, I think there's, right, well, there is a very nice categorical interpretation, and I haven't done it yet, but if you're interested, we could talk. Whenever I start reading about vibrations, I just sort of, I don't know, there's something about it that I just lose it. Okay. Any other questions? Okay, well, I think we're done, so thank you.